All right, welcome back. So this is going to be part 2 of our little brief review of chemistry. And so we want to talk about some of the important atoms that we're going to use here in zoology during this semester, and then also we'll talk about some functional groups. In biology, a few atoms make up the majority of molecules. So you got that whole periodic table and all that stuff that you work with in chemistry. And to be sure, you know, a lot of those elements are important here and there. But the majority of the chemistry we talk about is made up of only a handful of molecules, or a handful of elements, excuse me, that we're talking about right here. Hydrogen, oxygen, nitrogen, carbon. You could probably also throw phosphorus in there. You know, these are all at the top of the periodic table. They're all fairly simple, and it's just by, you know, combinations of these making these great big molecules, but only out of a few building blocks. That's most of biochemistry. Of course, again, other things can be important, but these are really the big players, and this is what we're going to talk about all semester. Now, the big player, the building block, all organic chemistry is based on carbon. And all living things are carbon-based. And so basically every molecule we talk about in here is going to start off with a carbon skeleton, and then we're going to just some variations on that theme. Okay, just a sidetrack. If we were not carbon-based, somewhere out there, if there's another planet that's got life on it, but it just happened to not have as much carbon as this planet does, what's another likely molecule that life would be based upon if we weren't carbon-based? The answer is silicon. So if you look in the periodic table, silicon is directly below carbon in the periodic table. Things in columns of the periodic table have similar chemical properties, right? And silicon also wants 4 electrons in its outer shell. It's got very similar chemistry, and so it's going to behave the same. And because carbon and silicon have 4 valence and can react with 4 different things at once, that gives them the widest variety of possible molecules that they could form. And so that's probably why living things are carbon-based, because you can get much more diversity if you're carbon-based than if you're based with something that has fewer reactions. Well, silicon, keep saying silicone, but it's silicon, would be the same thing. So, just an interesting side note. Okay, but here on Earth, organic compounds are made from carbon. Now you have lots of simple organic molecules, but you have lots of colossal ones, all right? Most organic compounds, again, start with a carbon backbone and lots of hydrogens. So hydrogen being, you know, a simple element and very reactive. Any time that you need an electron, you can usually find a hydrogen and react with it and share that electron. And so lots of our biological molecules are just carbon and hydrogen. And so you make this carbon skeleton, and then variations of that theme give you the different molecules that you need for life. And that's kind of what we're going to be seeing all semester. The carbon chains vary in length and shape, but that's very important to their function. And so, for example, here we've got a couple of different molecules, and they've got a carbon skeleton, and one's got 2 carbons and one's got 3 carbons, right? But they're very different molecules. Just adding that extra carbon, and you see how all these carbons are also bound to hydrogens. And so, again, that carbon wants to fill out its outer shell. The easiest way to do that is to just grab hydrogens, because, you know, hydrogens are everywhere. And so just adding that extra carbon gives you a completely different molecule with completely different properties. Now here we've got 2 molecules that have the same number of carbons in them, but they're arranged differently. You see, butane, they're all just in a straight line. Methylpropane, they are branched, different properties, different molecule. So just a very subtle change, even though they've got the same molecular formula, they got the same number of carbons, the same number of hydrogens. If those atoms are arranged differently, you got a different molecule and it behaves differently. Where the double bond is in the molecule can give it different properties. And so we've got 1-butene and 2-butene, and the numbers often tell you where the double bond is. And so if you look, the first one, the double bond is between the first two carbons, and in the 2-butene, the double bond is between the two middle carbons. Anyway, all you're doing, you got the same number of carbons, same number of hydrogens, just where that double bond is, different molecule, different properties. Now, something that we'll see a lot in organic chemistry, in a lot of chemistry, are these carbon rings. And carbon is such that when you start to, make a chain of it, when you get 5 or 6 carbons together, they start to bend around and form a ring. And again, this is just an energetically favorable state. And so 6 carbons in a straight line is pretty low energy, but in some situations, if they bend around and form a ring, it's even more stable. And so we'll see that a lot. And so what we're showing here is a couple of carbon rings. These are both 1, 2, 3, 4. Yeah, these are both 6 carbon rings. Sometimes you'll see a 5 carbon ring. Those are the most typical things, right? And so the carbons, don't have an end or a beginning, and you've got lots of hydrogens attached. And my point here is we're going to see this a lot. When we look at a lot of these molecules, you're going to see these ring structures, and I want you to understand it's just carbon forming up into these shapes. Now, usually we just draw the rings like what I've got indicated here. You don't want to have to write every little C and every little H, right? And so you just draw the shape. You just draw a 6 carbon ring, and you know that at each of those vertices, you've got a carbon. And you know that all those carbons also have hydrogens attached to them. That's the default. It's always like that. And so if you just draw a ring, then immediately from that ring, you know how many carbons you've got, you know how many hydrogens you've got. If you've got double bonds within the ring, you can see you've drawn kind of double lines, and the one and the benzene on the right, you got these double lines that kind of indicate where the double bonds are. So you've probably seen this before. You're going to see it a million times in this class. That's all it is, just a carbon ring. Okay. As we talk about our biological molecules, we're going to talk about different classes of biological molecules. And each class has its own properties. The first one we're going to talk about are hydrocarbons. And a hydrocarbon is exactly what it sounds like, a hydrogen and a carbon. But in fact, it's a bunch of carbons and a bunch of hydrogens. And that's it. No other atoms stuck in there, just hydrogen and carbon. Now, here's an interesting fact. It's starting to sprinkle again. Oh my gosh. Like I looked at the map and it said there's no rain coming. I really, really should have been a meteorologist, because you could just be wrong all the time and you still keep your job. It's frustrating. Okay, well, I'm going to try to get through this before it stops raining again. Starts raining again. Anyway, talking about hydrocarbons. Just carbon and hydrogen together. Now, hydrocarbons are usually very long chains of carbon and hydrogen, which means lots of covalent bonds, which means lots of energy. And so you're probably familiar with the term hydrocarbon. What are some hydrocarbons you know? Well, gas, oil, right? Natural gas. These are all hydrocarbons. And what do we do with all of those? We burn them for energy because they have lots of energy in a small package. They have what's known as a very high energy density. And so that's why hydrocarbons are important. And so that's what I mentioned. Fossil fuels are hydrocarbons. They all used to be living things. And remember, living things are all made of carbon, right? Those living things get buried for millions and millions and millions of years under tremendous pressure, and a lot of the other atoms react or disappear or go away. What you're left with is you just squeezing together all these carbons and hydrogens. They're all reacting, making these long molecules. all that energy in those covalent bonds is released when you dig it up and you burn it. And so that's why fossil fuels have so much energy. And so that's what I'm saying here. You know, all those bonds have energy. When you break them, you release that energy, and you can use that energy for other chemical reactions. And so hydrocarbons have tremendous amounts of energy. But again, where did that energy come from? Ultimately, it came from the sun. It went into a living thing. That living thing died and got buried. That energy is still in those bonds. And now we dig it up and we use that energy for other chemical reactions. Okay, last topic I want to hit on here, basically this idea of functional groups. Functional groups are unique small molecules that are just like a part of a bigger molecule, but that's where a lot of the magic happens. That's where a lot of the reactions happen. And the functional groups, the thing is there's only a handful of them that keep showing back up. Now, when you get into biochem and organic chemistry, you learn a lot more functional groups. But in general, especially in this class, there's only a handful of these functional groups, but they're very important because they are very reactive. And so we learn these functional groups and we learn to recognize them, and then over time you know their properties and you know their chemistry, and you start to understand things a lot better. And so here I just want to give you an example of what we're talking about. I've got a couple of organic molecules here, and you notice that these are big molecules. Like I said, like lots of biological molecules are big. They're both made of several rings. You see, they each have 3 6-carbon rings and 1 5-carbon ring, right? Again, every vertex of this pentagon or hexagon that you see drawn, every vertex represents a carbon. And most of those carbons also have some hydrogens attached to them. Okay, and you also see where you've got some double bonds between some of the carbons, just like I talked about. But I've got these 2 big molecules, and they have identical carbon frames, right? Compare the rings on these 2 molecules. You've got 3 6-carbon rings and 1 5-carbon ring. So they're identical frameworks. But they differ in their functional groups. They have different functional groups, and you also notice that by having different functional groups, it also changes the bonding. So if you look on the one on the left, it's got a few more double bonds than the one on the right, and that's because of the functional group. And so you've got an OH, which is a hydroxyl, in the estradiol on the left, and you can see they both have a couple of these hydroxyl functional groups. You've got a methyl group. CH3 is a methyl group. And so, again, they both have some methyl groups, but the testosterone has an extra one stuck in there. The oxygen, I can't remember if there's a name for the oxygen functional group. At any rate, they're very simple, but these are the things that interact with a lot of the chemical reactions. So these functional groups can be important. And so, again, in these 2 molecules here, for example, you've got identical carbon frames, very small difference in their functional groups, but that small difference makes very different properties. What are each of these molecules, right? These molecules are very similar, except they have just a subtle difference in their functional groups. But what do you have? You have estradiol and testosterone. Those are the sex hormones, and they have very, very different properties in your body. Right? And this is a theme that I'm going to beat into your brains. And I've already kind of started to hint at it. Small differences in molecules can have huge differences in function. And so, again, this is why we need to sort of understand chemistry. Because if you can understand that it doesn't take a very much difference. Here I'm looking at 2 molecules that are basically identical. They just have a little bit different functional groups. But man, do they have very different responses when they're in your body. The female sex hormone and the male sex hormone do very different things depending upon your body and all the other molecules in your body. That is a theme that I'm fascinated by, and so I bring it up over and over again. It only takes a very small change at the chemical level, at the molecular level, to get a very big change at the organismal or the functional level. So keep that in mind. Okay. That's the point that I'm trying to make right here in this last slide. Slight differences can have huge differences in living organisms, and we will return to this theme over and over and over again. And so that was my brief review of basic chemistry. Now we're going to start to apply some of those ideas and look more specifically at some of the groups. Again, all of this, there's a method to my madness. These are all things that are going to turn up again and again and again during this semester. So I just want to make sure we're all on the same page. Great. So I'll see you back in a little bit. And I think the rain has stopped, so I might keep going. Awesome. See ya.